Okay, so this is lecture 2 on our inverse trig. If we recall what we did yesterday, we looked at the tangent graph and we noted that the way the tangent is graphed is not invertible. We have all these asymptotes, and certainly this is not a one-to-one function, because if we try running a horizontal line, the graph fails the horizontal line test miserably. So we agreed that to make it invertible, we can eliminate all parts of the graph outside of this first central branch. And so now we're looking at just a piece of y is the tangent of x. Our restriction is that x has got to fall between negative pi over 2 and x is pi over 2. So that would be our domain, right? So let's do it this way. Domain is from negative pi over 2 to pi over 2. And the range just obviously is all reals, right? Because this branch goes all the way down to negative infinity and all the way up to positive infinity. And then after we did that, we inverted it. We found a graph of the inverse tangent, and that's the one that we're studying in this chapter. And these vertical asymptotes over here, this x is pi over 2, turned into a horizontal asymptote over here. This was y is pi over 2. Remember, we were swapping x's and y's. And likewise, the x is negative pi over 2 turns into y is negative pi over 2. And the graph, now look at the tangent graph, passes through the origin and starts to go up towards the asymptote. For the inverse tan, passes through the origin and starts to go up. This was the graph of the inverse tan, and if we wanted the domain and range, we just note that we're swapping, right? We're swapping the x's and y's. So the domain of the inverse tan was negative infinity to infinity, and the range was, in fact, negative pi over 2 to pi over 2. Okay? Note that because the domain is all reals, we could pick any number that we want. We could say, what is the inverse tan of 1,000,000? So here's my calculator. I'm in radian mode, and I hit inverse tan of 1,000,000. And I get that number. And so the question is, what is that number? Well, graphically, as I go further and further out this way, this curve gets closer and closer to this value. So we would suspect that this 1.5707 is very close to pi over 2. Let me punch in pi divided by 2. And sure enough, it is very close to it. It's off by, let's see, tenths, hundredths, thousandths, 10,000, 100,000. It's 1/100,000th off of pi over 2. So we're really close. And in fact, we could do that for any positive or negative value, okay? Because the arctan is defined for all reals. Make sure you know the graph. Make sure you're able to reproduce it with 3 points. We have a point here, which is 0, 0. And for these other points, we'll talk about those a little bit later in this video. Okay? So now the next object is to consider the sine and the cosine. And very similar, the sine x is not invertible the way it stands, right? Because we know that this wave goes on forever, and it would fail a horizontal line test miserably. Any horizontal line would hit it in multiple places, an infinite number of places. So not invertible, there is no inverse, unless we restrict the domain. And the standard restriction is to take away all the wave up to this first crest, and all the wave down here, down to this first trough, right, like that. And just consider this portion of the wave. Now, again, it is a sine wave, so you should not have any trouble figuring out the x and y coordinates for this point, nor for this point down here. So let's see, we know the amplitude of the wave is 1. And let's see, the period of the wave was 2 pi, right? So from here to here is 2 pi, this is 1 pi, this would be pi over 2. So pi over 2, comma 1 is that ordered pair right there. And this is negative pi over 2, comma negative 1. That's the ordered pair for that point. Okay, to find the inverse, we do pretty much like we did with the tangent. I guess I never did put the graph up here, or the equation. This is y is tan inverse of x, right? That's what we said. It's also called the arctangent, and why we use arctan we'll get to in just a little bit, arctangent of x. So for this one, we know the inverse is going to be the arc sine. So y is the sine inverse of x, or y is the arc sine of x. And the graph, we're going to swap x's and y's. So instead of having pi over 2, 1, we're going to have 1 and then pi over 2 up here, right? And instead of having negative pi over 2, negative 1, we're going to have negative 1 and negative pi over 2. You might want to note that, 1 is this distance. Pi over 2 is about 1.5, so I'm making this red vertical bar a little bit longer than the horizontal bar. This is about 1.5 units up. Okay, so how do I graph it? Well, I need to go through these points. And again, look at the sine wave. The sine wave goes through the origin and bends down to that point. This one will go through the origin and bend up to that point, like that. Okay, and likewise over here. So this is the graph of the arc sine. If we wanted to talk domain and range, and if you knew the domain and range of the sine wave, then you would be okay. So the domain, now remember we restricted the domain. So we said we're only going to be going from negative pi over 2 out to pi over 2. This time it will be inclusive, right? There's no vertical asymptotes here. We actually include that point, pi over 2. And the range, of course, is negative 1 to 1. If we go back to this arc sine for the domain and range, we simply swap these guys, swap the x's and y's. So the domain is negative 1 to 1, and the range is negative pi over 2 to pi over 2. Okay, so yeah, you should know that. If you graph it on your calculator, it's sort of interesting. Let me clear this off. If I do, give me the arc sine, or y equals the sine of x, and I look at it in a standard window, which is zoom. This is the standard window. We just get this little tiny piece right there, right? If I zoom trig, that doesn't do much better. We still get this little tiny piece. It's this green graph over here. If we were to continue graphing the wave, now remember this wave, the sine wave, goes like this. If we were to continue graphing this, the wave would look like that. So when you draw this arc sine, make it so that this point right here is as if it were at the top of a wave. The graph on the calculator is a little misleading. It almost looks like it goes up and stops like that. But no, it actually goes up and starts to go vertical, right? Because we know it's going to end up going around. Okay, so there's the arc sine. How about the arc cosine? Again, very, very similar development. We look at the cosine wave and we notice that it is not invertible, right? Fails the horizontal line test miserably. So we have to restrict it. This is why it's cosine of x. This is going to be the cosine inverse of x. Here it is on the calculator if you just want to take a look-see. Cosine inverse of x graph. It's sort of another little tiny piece of a wave. So what's happening? What we're going to do is we're going to restrict this cosine from here to here, just like that. That's the standard restriction. So we'll take away that part of the wave and that part of the wave. Now this red section is in fact 1 to 1. And let's see, this is pi. You might want to verify that. This one is pi over 2. If we wanted ordered pairs, this ordered pair would be pi comma negative 1. We know this wave goes down to negative 1. This ordered pair is 0, 1. And the 0 of this cosine function, this ordered pair where it crosses the x-axis, would be pi over 2 and 0. If we wanted domain and range, not terribly hard to do. We restrict the domain from 0 to pi. The range, we know it's a wave, so negative 1 to 1. When we go to the arc cosine or the cosine inverse, all these points get swap x and y. So instead of 0, 1, we're at 1, 0. 1, 0. Instead of pi over 2, 0, we're at 0 pi over 2. So this would be pi over 2 up here. And instead of pi negative 1, we're going to negative 1, but all the way up here at pi, which is right there. And then again, we have to connect these with a smooth curve. It looks like that. Okay. And if we needed the domain and range, again, we just swap x's and y's. So if you know it for the wave, it's real easy to put it down for the inverse function. Okay. So far, so good. Now, let's look at some problems. I'm going to assign some problems tonight out of section 8.1. 8.1. Let me grab my book here. Okay, so I've got my book, and it's not 8.1, it's 7.1. We're working in section 7.1. The assignment's going to be on page 463, and they're going to be the problems. Let's see if we can knock out 15 to 25. 15 to 25. I'm going to let you do those tonight, but I want to look at some of the even numbered problems. So here's number 16. 16 says, without a calculator, figure out what the cosine inverse of 1 is. You say, wow, how am I supposed to do that? Okay, so here's the approach on all of these types of problems. Consider a unit circle. Okay, so we have our unit circle. And now instead of reading this as cosine inverse, read it as arc cosine. So let's see, arc cosine of 1. Okay, so that's the one we're trying to figure out. Now, how does that get translated in your head? This is what you're trying to find. What is the arc whose cosine is 1? That's what you're trying to find. Okay? Now, you can think arc. You can also think angle if you really want to do angles, although I sort of prefer arcs here. So what is the arc? Okay, so we've got our unit circle, and we know that we can travel around various ways. We did note, however, for the arc cosine right here, the range is from 0 to pi only. So these are the angles that we're talking about. And again, we say angles. Y is the cosine of x. This x, that is the angle, right? It's the angle whose cosine you're trying to find. So x, these are angles. And when we swap, these now become angles. Or if you want, you can think arcs. Okay, so yeah, our angles between 0 and pi. So that when we look at this circle, we really only need to be concerned with the top of the circle. Starting from 0, that's an angle or an arc. Remember, this is pi over 2 up here, and this is the arc or the angle pi way over here. So now the question is, what is the arc that has a cosine of 1? Well, we know our unit circle. We know that this ordered pair over here is 1, 0, and that the cosine is the x-coordinate. So the arc that has a cosine of 1 is, in fact, 0. Here's a similar problem. What is the arc that has a cosine of 0? What is the arc that has a cosine of 0? So again, we think about the top of the circle, because that's where the arc cosine is defined. And up at the top of the circle, we know the ordered pair is 0, 1. And this arc that goes from here to here is, in fact, pi over 2. So that would be the answer. The arc cosine of 0 is, in fact, pi over 2. Suppose we wanted the cosine inverse of 1/2. Well, let's make it negative 1/2 just to make it a little bit more intriguing. Okay, so remember how you think about this. This is the arc that has a cosine of negative 1/2. Okay, so we're looking at the top of the circle. That's where the arc cosine is defined on. And let's see if we can clean this up a little bit. we want the cosine to be a negative 1/2. Well, okay, so here's our circle. Cosine is the x coordinate, and it's negative 1/2. It's right here. This is the arc, or the angle that we would be needing, right? Because the ordered pair there is negative 1/2. I don't care about the square root of 3/2. But what is this arc? Answer 2 pi over 3. If you know your unit circle, these problems are pretty easy. Okay, so there's some arc cosine problems. Let's try some arc sine problems. So let's see. Problem number sine. Problem number 24. So 24. And again, you'll be doing the odds. This is an even. Number 24. It says find the sine inverse of minus the square root of 3/2. And what does that equal? Okay, so first of all, let's go back and look at our arc sine. We noted that when we're dealing with the sine wave, this was called the angle or the arc, right? It was x. That was this value down here. And we said that the angle of the arc was always between negative pi over 2 to pi over 2. Right? That's how we restricted that domain. So when we come over here, we're only going to be dealing with the right half of the circle. So negative pi over 2 is down on the bottom, and pi over 2 is up here. And so we're just dealing with this right side of the circle. So whenever we're dealing with arc sine, consider just these arcs, these angles. Okay, so let's see. Here's the problem. What is the arc sine? What is the arc that has a sine of negative square root of 3/2? Well, that number certainly looks familiar. Let's see. That was the number that paired with 1/2, right? We're dealing with the right side of the circle only. Okay, going this way, this is pi over 2. Coming down as a negative would be negative pi over 2. And let's see, the sine is negative. Let's see, this would have been 1/2, right? So this would have been the ordered pair 1/2 positive square root of 3/2. We want 1/2. Actually, we don't care about the 1/2. We care about the sine is a negative square root of 3/2. Okay, so this in fact is where we are in the circle, and the task is what is that arc? What is that angle? It's 60 degrees in the negative direction, so negative pi over 3. You should answer these things in radians, not degrees. It doesn't hurt to think degrees, but yeah, these are typically answered in radians. Okay, so and you've got, well, let's do one more since we've got it here. What is the arc that has a sine of 1? So what is the sine inverse of 1? Sine inverse of 1. So I say, okay, sine was the y-coordinate. Where on this circle, on the right half of the circle, is the y-coordinate 1? And that would be all the way up at the top, right there. And what is that arc that gets us there? That would be pi over 2. One last thought on before we leave the arc sine. Suppose you were given this. What is the sine inverse of pi over 3? Okay. Now, let me just jump in my calculator here for a minute. And I'm just going to try this and watch what happens. Let's see, pi divided by 3. Sine inverse of pi divided by 3. And it says, sorry, you can't do that. It's outside of the domain. You go, whoa, 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 what's going on here? Well, let's see. What is pi over 3? Pi over 3 is about 1.04, correct? So this is asking, what is the sine, or what is the arc that has a sine of 1.047? Well, I mean, we know this is a unit circle, right? How big does that circle get? It gets up to 1. It never gets up to 1.047. All right, so this is undefined. This doesn't make any sense. This expression is undefined. Again, if you go back and look at when we played with arc sine, right, this is now the x value, right? This is the x value. We're putting that into the arc sine function. So here's a picture of our arc sine. Let's see. Over here on the wave, x was an angle, but then we swapped. So now the angle is going to be y, okay? So this is going to be our angle because we swapped x and y. Likewise, y over here was the actual sine value. That's how high the wave went. The wave went up to 1, down to -1, right? Up to 1, down to -1. And when we swap, that's over here. So this thing has got to be between -1 and 1. You cannot put in 1.04 in there. That's outside of the domain. And that's what we said, right? The domain of this arcsine always had to be between -1 and 1. And you're not allowed to put in 1.047. Okay, so just be careful. There's going to be some tricky problems like that. Okay, so we've done arc cosine, arc sine. Let's try an arc tan. So I'm looking at problem number 20. Number 20, it says, without a calculator, find what the tan inverse of -1 is. Okay, so no calculator. We'll pretend like we don't have that. We need an arc whose tangent is equal to -1. I need an arc on the unit circle. Now, where on the circle are we? So again, we go back to when we first put the tangent together, like that was yesterday, and we said, okay, these were our angles, right? And the angle always fell between -pi/2 to +pi/2, but not including that. So how does that translate to a circle? Well, again, we're on the right side of the circle. So yes, we're on, but now we cannot get down to -pi/2, nor can we get up to +pi/2. So just think the right side of the circle only. And those angles will always fall in between -pi/2 and pi/2. Okay, so here's our problem. And we want the tangent to be negative. We're considering just the right half of the circle. Let's see, tangents are positive up in this quadrant. Down in this quadrant, we know the tangents are negative. And in fact, this -1 should be screaming at us. We know this ordered pair of √2/2, comma, -√2/2, right? That pairs up with -pi/4, right? And so the tangent of -pi/4, the arc that has a tangent of -1 would be this guy right here, right? √2/2, √2/2 with a negative. So this is -pi/4. Of course, you can check these if you want. You know, you can do sort of like what we did with the triangles. If I said, what is the tangent of 45 degrees? Or what is the tangent of pi/4? You probably would have said, okay, I know what a 45-degree angle looks like. That was one of my basic angles in geometry. Remember this 45, 45, 90 triangle? It was an isosceles triangle. These were the same length, right? Think of a square cut in half. So all the sides of a square are the same, cut it in half. These are obviously the same, okay? So if I pick the acute angle, 45 degrees, right down here, and the tangent of 45 degrees is opposite whatever this is, divided by this, they're the same number. So it's A over A. The tangent of 45 degrees is 1. So if I need an arc that has a tangent of 1, that would be 45 degrees. The drawback with the triangles is we never had negative length. So that's why we stick with the unit circle approach. This one is requiring the tangent to be a -1. So yes, the unit circle will get us there. It's very similar to the triangle, but triangles are sort of limited to that first quadrant where x and y are both positive. Here we need the y value to be negative and the x value to be positive. So it's sort of like this triangle in here, and calling that a -45 degrees. My geometry teacher would throw up, right? Because he never had negative angles in geometry. But sure enough, that arc of -pi/4, -45 degrees is what we need, right? That ordered pair, again, being √2/2 and -√2/2. Okay, so for all the ones that say no calculator, suspect that you're dealing with a standard angle, one of the angles on the unit circle that you've memorized. So pi/6, pi/4, pi/3, pi/2. And for the arc cosine, you're always going to be dealing with the top of the circle, right, from here to here. That's arc cosine. And for the arc sine, you're going to be dealing with the right side of the circle. And then for the arctan, you're also dealing with the right side of the circle, but you have to exclude the tops and bottoms. So that should be enough to get you started. Practice some homework tonight. I'll, again, post the homework soon, and I will post the solutions around supper time. Work the problems, look at the solutions. In class tomorrow, ask questions first. I'll try to clear up all the questions, and then we'll have a short quiz tomorrow just on a couple simple unit circle type problems. Okay, I hope that helps.